Okay, so we just understood how the classical Maxwell theory works. We now want to understand the quantum theory. And so what that means is that we're going to study the following path integral. We are going to path integrate over the gauge field. And the weight in the path integral is, of course, going to be e to the I times the action of interest, which in this case is the Maxwell action. So the action of the free Maxwell theory. Okay. We're going to eventually be interested in quantizing theory with the fermions too, but for now we'll understand the implications of this action first. Okay. So as we know by now, the propagator, we want to find the Feynman propagator for the photon, and the Feynman propagator for the photon always comes from inverting the quadratic term in the action. So let's do that. Let's write this action. This is a quadratic action. Let's write this in a useful way. Okay. So the action I can write is equal to the integral d4x times minus 1/4 d mu a nu minus d mu a nu times d mu a nu minus d nu a nu, where all I'm doing here is expanding f mu nu in terms of its definition in terms of a. Okay, so now this isn't in quite the right form. To make it be in the right form, I should first note that there are basically two kinds of terms here, each of which appear with equal weight. So if I group the terms together, and if I then integrate by parts, then you can see that this is equal to the following. There's one term like this, and there's one term like this. Okay. Where to go from here to here, what I did was I combined terms and then integrated by parts. Okay. And finally, I can write this in a sort of more aesthetically pleasing way. In particular, it's nice to write this like a quadratic form, acting on A, sorry. So you can convince yourself that this thing is exactly equal to this. Okay, where it should be pretty clear that the first term comes from here, and this term comes from here. And you can check this just by expanding everything out, of course. Okay, so whenever we do a functional integral, what we want to do is invert the differential operator that appears in the action. So in this case, that differential operator is this guy. So what we want to do is invert that. So the Feynman propagator for the photon, in other words, the Feynman propagator for the field A, is the solution to the following problem. I just follow the normal rules. I write down the operator appearing in the action, and then I demand that it acts on something, some propagator, where this propagator now has a nu and a rho index because it propagates a vector field. And this should be equal to the identity. So the identity now is an identity both in the Lorentz index space, in the mu nu space, as well as an identity in position space, hence a delta function. So this is the problem we need to solve. Okay? Now you might think we can just go ahead and solve it, but actually it's not so simple. In fact, no such d mu nu exists. And this is because the differential operator in other words, this operator here has no inverse. How do we see that it has no inverse? A simple way to see this is to go to momentum space. So in momentum space, by the usual tricks, the equation above becomes, each d nu becomes a p basically. And so we have df mu nu of p equals to minus I delta mu nu. It's just the momentum space version of the integral above. But in fact, this matrix has many zero eigenvalues. To see that, let's act with this matrix, with this guy, on a function of the form p mu times alpha of p. Okay. So what happens if we do that? Where here alpha of p is any function of the momentum p. Let's just see what happens. So I'm going to act with this on p mu alpha of p. So what do we find? Well, this term here just raises the index on the p mu and makes it a p nu. This term here, the p mu and the p mu combine together to give me p squared, and so I have minus squared minus p squared p nu, and thus this is equal to 0. Okay. In fact, this is equal to 0 for all choices of the function alpha of p. So what that means is the differential operator has a non-trivial kernel. And if you recall what that means that it cannot be inverted. Okay. So what's going on here physically? Physically, the point is that the issue is coming from the gauge transformations. So imagine a field configuration that is pure gauge. Okay, in other words, A is the gauge transform of 0. So it's just the derivative of some scalar function. This is a so-called pure gauge transformation. Pure gauge solution. Okay. Now, this pure gauge solution has f mu nu equals to 0, which means that the action of this equals to 0. But what that means, when you integrate over this pure gauge direction, so when you integrate over some sort of pure gauge field in your functional integral, the integral normally goes like e to the is, and s oscillates very, very quickly, and that wipes the integral out and makes it go to 0, or at least converge. Let me just say it makes it converge, because this thing oscillates so quickly. There's no such suppression here. There's no oscillation. So in fact, nothing suppresses these pure gauge directions in the functional integral. And so the integral over these pure gauge directions results in a divergence in the functional integral. And so this divergence is what we're seeing. This is why the propagator can't be inverted. Okay. Now, you see, clearly we're doing something wrong, right? Let's take a step back. You see, we're integrating over things that are pure gauge, but remember, things that weren't gauge invariant were not physical. So if we integrate over all these pure gauge directions in the functional integral, it's kind of like we are integrating over a bunch of non-physical stuff, and it's this non-physical stuff that's making the functional integral diverge. We need to find a way to rearrange this integral so that we integrate only over the physical stuff. Okay? So in other words, a more fancy way to say it is we want to factor out the pure gauge directions in the functional integral. There's a way to do this. The trick to do this is called the Faddeev-Popov procedure. So let me now explain what this Faddeev-Popov procedure is. So this is basically a quantum analog of the gauge fixing that we did earlier. Okay, so it's quantum gauge fixing within the path integral. So let's let g of a be a function that we want to be 0 for gauge fixing. So for example, if you recall earlier, we studied Lorentz gauge, where d mu a mu was equal to 0. If we were doing Lorentz gauge, we would say that g of a is the function d mu a mu. Okay? So this is the Lorentz gauge choice for G of A. Now, the point is, we want to use this gauge fixing function to sort of project out some stuff in the path integral. To do this, I have to introduce a new mathematical thing. Let me introduce the concept of a functional delta function. Okay. So what is a functional delta function? So this is a functional, which means that it's a map from the space of functions to the numbers. Okay. And so basically, it's something like delta of phi. And it satisfies the following properties. Delta of phi, which is a map from functions to the real number, so you stick in some function phi and you get some number out, it's equal to 0 for all functions that are not the zero function. Okay. And furthermore, it's also true that the functional integral over all phi of the functional delta function is equal to 1. So it should be clear, this is just the functional, fancy functional version of delta of x. Okay? Recall delta of x, the normal delta function, is a function which is 0 almost everywhere. That's like the first thing. Yet its integral is still 1. That's the second thing. You can very loosely think of this delta function. I'm going to put this in quotes. It's only very loosely true. You can think of it as being a product of ordinary delta functions, the one-dimensional delta function, at all points in space. Okay. I don't really want to focus on this. This is I mean, this delta function in all points of space. And I don't want to focus on this. This is only very loosely true, but if you want, you can imagine this is what's happening. It kills the input unless the input is exactly equal to the zero function. Okay. So what we want to do is somehow stick in a functional delta function which is delta G of A into our functional integral. If we can do that, it will kill all the gauge field configurations that don't satisfy the gauge fixing condition. And that will hopefully solve our problem. So we want to do this, we want to do this in a correct way. Okay? So first, let me define the following object again. Let me define A superscript lambda. So A superscript lambda is just the gauge transformed version of the field A. So I take A and shift it by d lambda. This is the gauge transformed. Version of A. Next, what we do is we now consider the following very, very fancy way to write the number 1. Okay, so here we go. So here is a way to write the number 1. 1 equals to the integral over all gauge fixing functions times a delta function g of A of lambda times the determinant, the functional determinant of delta G A lambda d lambda. Okay. So this is maybe not obviously 1. Let me write down a finite dimension of this to make you feel a little bit better about it. So compare this to the following. Compare to the following slightly simpler way to write the number 1. Consider the integral of delta y of y, where this is just a normal delta function. This is 1. Now, if you do a change of variables in the integral, you can see that this is equal to delta of y of x times dy dx. Okay? This is still equal to 1. Now, the fanciest way of writing 1 here, this functional version, is basically the same thing, where the role of y is played by g of A, and the role of x is played by d lambda. Okay? If this is confusing, I encourage you to pause the video now, take a step and make sure you agree that this is indeed 1. Note the functional determinant plays a crucial role here. It's basically the same thing as this here, which would have been a determinant in higher dimension. The determinant is the Jacobian factor that you find when changing variables from lambda to a, or lambda to g. Okay, so this is 1. And now let's insert 1 into the functional integral in this fancy way. So what do we have then? Well, the partition function always had an integral dA. It now also has an integral d lambda times delta g of a lambda times the determinant, functional determinant, delta g a lambda delta lambda, times the normal action, which was e to the I s of a, where s of a here is just the Maxwell action from above. Okay. Okay. So what next? So to proceed, we need to actually fix a convenient gauge fixing function. So the one we're going to pick is the following. So I'm going to pick g of a to be d mu a mu, and this is coming from the choice of Lorentz gauge. And then I'm going to say that d mu a mu is not actually 0, it's in fact equal to omega. And this is a perfectly good gauge fixing function. I'll explain why this omega is there later, but this is just the gauge fixing function we're going to use. It's a little bit more complicated than normal Lorentz gauge, but we'll see it's the same idea. Okay. So it really doesn't matter what this function is, because you can pick any gauge you like to do your functional integral. So there is something nice about this choice. Let's figure out what this quantity is. The functional derivative of a of lambda with respect to lambda, of g of a of lambda with respect to lambda. Okay, so what is that? So let's just go through the steps here. So what is this? Well, this is the functional derivative of what happens if you stick a gauge transformed into here. A gauge transformed is, of course, a nu plus 1 over d nu lambda. Excuse me, there's a minus sign wrong here, doesn't matter. And then we subtract off the omega here. Okay, so what is this? Well, the lambda only appears here, and so this whole thing equals to just delta squared over e with a minus sign. Okay. So in other words, this functional derivative is this operator, the operator delta squared. Okay. In other words, it doesn't depend on anything. All right. That's kind of nice because that means that when we compute its determinant here, we can take the whole thing outside the functional integral. So what do we find then? So if I now compute z with this choice of gauge fixing function, which I'm going to denote z sub omega, just to remind you this omega is from g, which depends on some arbitrary function omega, then what I can do is I can take this determinant and move it outside. So because the determinant is just the determinant of minus delta square over e, I get that. And now I still have to do the integral over lambda and over a, and I still have this delta function g omega of a lambda, and I still have an e to the is of a. Okay, and I've put some omegas in the subscripts just to remind us that things here in principle depend on omega, although in the end they really should not. Okay, now what next? Remember that a lambda is a gauge transform of a. And the action S of a is gauge invariant. So in other words, I can write that S of a equals to S of a lambda. So what that means is What that means is that I can stick over here a lambda and just make this S of A lambda instead. The two things are exactly equivalent. Because that was quite small, you might not have seen it. Let me write this out explicitly. I used to have an e to the I S of A there. Now I have an e to the I S of A lambda. Okay? That's what happened right now. And next, note that the measure, the integral measure itself, is also gauge invariant. And that's true because it's just a constant shift of A. Okay? So point-wise, you can shift A in a constant way. In other words, I can also put a lambda here in the measure. Again, that was quite small, so let me write it out again carefully. I'm taking dA and making it dA lambda. Now notice that everywhere in this integral, there is never an A by itself, only an A lambda. So finally, for my last trick, let me rename A lambda back to A. Well, which I can do, that's totally fine. After all, this is just a variable that I'm integrating over. I can call it whatever I like. After doing all those steps, what I find is that z sub omega is equal to the integral 1 over e delta squared, integral d lambda, integral dA delta g omega of A times e to the I S of A. And this is the nice thing, because note now that all of the integrals over lambda have completely factored out. There's no integral over the auxiliary gauge parameter lambda anywhere in this integral. Okay? And so all that this does is introduce some sort of a constant prefactor, which I'm just going to call n from now on. N is infinity. In a sense, it's the integral over the volume of the gauge group, but that doesn't matter. We're not going to worry about it. And so if I now put back in the definition of g omega, what I find is that z of omega is equal to some sort of a constant factor n times the integral dA times the following delta function. Okay. So we are almost done. We're just going to do one more thing. Note that my notation suggests that things depend on omega, but at the end of the day, nothing should depend on omega, because omega is just a gauge fixing parameter. So what I'm going to do is the following thing. I'm going to integrate over all omega. With a Gaussian weight. Why not? Okay. Okay, you'll see why I'm doing it in a second. But let's just do that. So if I do that, then my partition function becomes infinite constant, let's not worry about it, times integral over all omega, integral over all A, times the exponential of minus I, integral d4x, 1 over 2 zeta, omega squared, times delta function, d mu a mu, minus omega of x times e to the I s of a. Okay. Now, the point of me doing this kind of weird thing where I integrated over all omega with a Gaussian weight was really to make it possible to solve the delta function constraint in a simple way. Notice that this delta function constraint says that omega is equal to d mu a mu. So if I integrate over all omega, I can solve the constraint and just replace this omega here with d mu a mu. And what I then find is that the gauge fixing parameter, if I solve the delta function, that does the integral over omega, takes care of it, and I just get that the integral is now the integral of the Maxwell action minus a factor of integral d4x, there's an I over here, times d mu a mu squared over 2 zeta. Where from here to here, I used this delta function to set omega equal to d mu a mu. Okay, this is great. This is what we call the gauge fixed form of the path integral. Okay. Note that all of this stuff, all the work that we did, everything, just basically added an extra term to the action, where that extra term is d mu a mu over 2 zeta. D mu a mu squared over 2 zeta. In other words, the effective form of the Maxwell action has been modified to now be the following, which I'm going to call FP for short. The Faddeev-Popov form of the Maxwell action is now whatever was there before, which is just minus 1/4 F mu nu, minus this extra bit, 1 over 2 zeta, delta mu a mu squared. So all of this has added a gauge fixing term to the action. Sort of the slick way that we did it sort of guarantees that everything is okay in the quantum theory. Okay. So now it turns out we can indeed invert this propagator. Okay. So to do this, what we do is we go to Fourier space. Okay. Or sorry, let's not do that yet. Let's first write this in a nice way. So if I write this in a nice way, if I integrate by parts on this, then what I find is that this Faddeev-Popov action takes the form integral d4x 1/2 a mu delta square eta mu nu minus 1 of zeta delta nu a mu. Okay, and this comes again from the same sorts of things that we did previously, just now taking into account the extra bit coming from this term. Okay, the part with the 1 was already there. This is new thing is coming from the gauge fixing term. Okay, so now we can invert this to find the propagator. Okay. So the way to do this is to first go to Fourier space. In Fourier space, the equation we want to solve takes the following form. It's minus p squared eta mu nu plus 1 minus 1 over zeta p nu times df nu rho equals to I delta rho nu. This is again the same equation that we saw before, except with the crucial new addition of this 1 over zeta term. Now, I want to solve this formula, this equation for df, which is a 2-index object. Now, this kind of computation comes up over and over again in field theory, so I'm going to show you how to do this. So basically, let's consider what is the most general form of df. Okay. So df nu rho as a function of p, this is a tensor object. It's a 2-index tensor object. What are the possible 2-index tensors we have to play with? Well, the only two objects that we have to play with are, if you think about it, the metric, so there could be a term like eta nu rho, and p. So what I could do is I could take p, a 1-index object, and make a 2-index object out of that. And now there are two coefficient functions here, a of p and b of p, which can have an arbitrary dependence on momentum, and I've put a factor of p squared in the denominator here just to give a and p the same dimension. This makes the final thing look nicer. So next, what you do is take this form for d of f and plug this back into here and expand out everything and see what you get. Okay. So if you do that and expand, then you can find that there's a couple of terms that you get. So on the left-hand side, you get a term like this, rho mu plus p mu p rho A of p, 1 minus 1 over zeta, minus b of p over zeta, and this whole thing is equal to I delta rho nu. So this is the right-hand side of the formula above. Okay, and now you can solve this for A of p and b of p. As an aside, it's immediately clear that if you take zeta to infinity, okay, then there's no solution to this, which is what I meant when I said that the old propagator without the gauge fixing term was not findable. In other words, the differential operator could not be inverted. So if you now demand this, you see that you have to adjust the coefficient of b of p to exactly cancel the coefficient of a of p, and then the coefficient of a of p is fixed by demanding that this thing be 1. If you go through that little exercise, what you find is that a of p equals 2 minus I over p squared, and b of p equals to minus I over p squared, zeta minus 1. And I'll leave you to go through that algebra yourself. The upshot is that the propagator for the photon is finally minus I over p squared, eta mu nu minus 1 minus zeta, p nu over p squared. So this formula right here is the Feynman propagator for photons, sorry. Feynman propagator for photons, which you have seen before, but now which we have very carefully derived from first principles in quantum field theory. Okay, so that pretty much closes the story. Okay, so basically you might wonder, what about zeta? What's the deal with zeta? What value do you use for zeta? So because of the way we derived it, zeta is just a gauge fixing parameter. The value of zeta doesn't matter. Okay? In other words, your final observable answer must not depend on zeta. It must be independent of zeta. So people who are very good at calculating things often keep zeta arbitrary throughout their calculation. Then at the very end, they can check to make sure zeta canceled entirely. That means the calculation is correct. People like me who are a little bit less good at calculating often set zeta equal to 1. This is called Feynman gauge. Okay? And that's nice because if you set zeta equal to 1, then this whole term from the propagator just goes away completely. You just have this term left over. Okay? But your answer must be independent of zeta. Indeed, different choices of zeta are different for different things. Okay, so that's it. This is the Feynman propagator. Okay? So if you recall, we were actually interested not in just pure Maxwell theory, which is what we studied all this time, but in the full action of QED. So if you want, we can now put the fermions back. So you get the QED action. And what you have then is that you have an action which depends on psi bar, and A, the action is the Maxwell bit that we just analyzed to death, and there's a term here, but actually let me expand this out. Delta nu plus I E A nu, and finally there's the mass term for the fermion. So this was the action for QED, which I've written out. This thing here, of course, is the covariant derivative, d nu. And from here, you can basically read off the Feynman rules. So to get the Feynman rules, you have the fermion ones from last time, and then the new addition for the gauge field. So I'm not going to write down the fermion ones again. What we just found is that there is a gauge field propagator, which propagates mu to nu, and we have just carefully derived that that gauge field propagator is minus I over p squared, eta mu nu, minus 1 minus zeta, p nu, over p squared. And there's also an interaction vertex coming from the term here, which mixes A with psi bar and psi, I will leave you to check carefully for yourself that the vertex for the interaction, which has one photon coming out and one fermion coming in, takes the form minus E gamma mu. And you can check this using the normal techniques that we know and love by now. In other words, take a functional derivative with the source, blah, 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 and so on and so forth. Okay. You can check this. The gauge fieldiness of A mu does not introduce any new complications in this case. Okay, so that's it. These are the QED Feynman rules, and of course there's the rules of the fermion from before. Okay, so I believe you worked with these extensively already in your QED course. Now you've seen carefully where they come from. So I want to say just one more thing. Notice that the interaction, this interaction vertex, its structure came from the structure of the gauge covariant derivative. And the gauge covariant derivative structure was fixed by a sort of symmetry property. This is an underlying theme, the fact that the structure of the interaction is fixed by the gauge symmetry. Okay? In other words, if you have gauge symmetry, you need to have this interaction. So this is an important principle which will become even stronger when we go on to non-abelian. Okay? Okay, and that's it. That's all for now. In the next video, I will carefully just tell you a few things that I didn't cover, and then move on to non-abelian gauge theory. Okay, that's all for today.